This reference guide will look at the first method for solving linear systems, which will involve graphing. Now, over the course of this year, starting in Unit 5 and certainly a lot in Unit 6, we've looked at graphing lines. What we're going to do now is we're going to apply what we've learned, and we're going to graph lines to find a point of intersection. So what we're going to be given, as we know with linear systems, is a pair of equations. Now, in order to find a solution to the two variables in the pair of equations, we're going to start by first putting each line that can be used from each equation onto the graph. And what we're going to find when we do that is there's going to be a place where our two lines intersect, a place where one line crosses over the other. That's what's known as our point of intersection. It's where the two lines meet. The coordinates of the point of intersection will be our solution to the variables in the linear system. So it's a really nice little technique where we can actually come up with our answer without doing much in the way of algebra. We can simply arrange an equation in a way that it can be graphed, look at the graphs and where they intersect, find the coordinates of that point of intersection, and that will spit out our answer. We can check that answer, and we'll look at how we'll do that when we do some of the problems found in this reference guide. All right, so the first bit of information gives us our steps for solving linear systems by way of graphing. The first thing you're going to do is you're going to look at the equation of the lines you've been given. What we want, ideally, is for these to be in slope-intercept form. So that is the form y equals mx plus b. So if we can, and we will be able to, we're going to arrange it in the form y equals mx plus b if this hasn't already been done for us. Remembering that m means slope, or m represents slope, and b represents the y-intercept. So once we have it in the form that we want, that is y equals mx plus b, we're going to plot each of the lines, ensuring, of course, that we start at the y-intercept and use the slope to create an accurate graph, or an accurate line on our graph. Then we're going to identify the place where they intersect, and we're going to write the coordinates of this point, remembering with coordinates that whatever's on the horizontal axis, or the x-axis, gets written first. Whatever's on the vertical axis, or the y-axis, gets written second. And these coordinates represent the x and y values for the linear system. Now, we may not be using the variables x and y, so what that is meant to say is that the coordinates will represent, the first coordinate will represent the solution to the variable you've placed on the horizontal axis. The second coordinate will represent the solution to the variable you've placed on the vertical axis. Again, we'll see what this looks like when we do some graphs here in a minute. And then you can ensure that you've done this correctly by putting the coordinates that we found back into the equations that we were given and making sure that it works for both of the equations. So let's look at an example that's done for you, and then we'll start doing some together. So we're asked to solve this linear system graphically. So the equations are x plus y equals 8 and 3x minus 2y equals 14. And when we're asked to solve it, that means find what the variables represent. So x is going to be the same value in both equations, and y is going to be the same value in both equations. But there's only one value that works for x and y. So we have to find the combination of x and y that will work with both of the equations that are given. So when we look at x plus y equals 8, well, that's a pretty easy one to put in the form y equals mx plus b. We're just going to move our x over, and that gives us our equation. So our y-intercept is going to be at positive 8, and our slope is going to be negative 1. Again, there's no coefficient written in front of x, so it's assumed or it's known that there is a 1 there. And we can see this represented in the red line that's on the graph below. It starts at 8, at positive 8, and it goes down 1 over 1, down 1 over 1. So that's a pretty easy one to put in the form that we want. Now the second one is a little bit more difficult, but again, nothing that's unmanageable. So 3x minus 2y equals 14. So I'm just going to move my 3x over. And divide out the negative 2, because we want y, of course, on its own. And what that will leave us, we'll have to go over here for this, it's going to leave us with y equals 3 over 2x minus 7. So that means up 3 to the right 2 for our slope, and negative 7 for our y-intercept. And you can see the blue line on the graph that's shown there includes that information. So now we look right here. That's the place where our two lines have intersected with one another. That's the place where they've crossed over. And we identify the coordinates of that. Well, those coordinates are at 6 on the x-axis, or the horizontal axis, and 2 on the y-axis, or the vertical axis. So 6, 2 is our answer, or is what we are saying is the answer to this problem. So we can confirm that that's accurate by plugging 6 and 2 into each of the original equations. And that, you can see, is being done right here. So the values have been plugged into the equation, and then it checks out. So we see that in the top one, when we plug 6 in for x and 2 in for y, we get 6 plus 2 equals 8. Well, 8 does equal 8, so that makes sense. In the next one, we plug 6 in for x, so we get 3 multiplied by 6, minus 2 multiplied by 2 should equal 14. 18 minus 4 equals 14. 14 equals 14. So it checks out, and that's what you want to have happen. And just an important reminder here, make sure you check it with both equations. So you may get a point of intersection, and it may work with one of the equations that you're given, but it may not work with the other. So the only way to ensure total accuracy is to make sure that you check your answer with both equations that were given. All right, so now we're asked the same thing. Solve the following linear system graphically. So let's start with the top one. So first thing we need to do is we need to put this in the form y equals mx plus b. So we move our 2x over by subtracting 2x from both sides. That leaves us with 3y equals negative 2x plus 3. Of course, divide out our coefficient of 3. Gives us y equals negative 2/3 x plus 1. So we have that in the form y equals mx plus b. We know the y-intercept is going to be at 1. And we know the slope is going to be down 2 and to the right 3. So we start by identifying our y-intercept. And then we go down 2 to the right 3. So our next point is going to be right there. And our final point, down 2 again. Oh, let me just correct that last one. Down 2 to the right 3. And then down 2 to the right 3 again. Puts me at negative 3 and 6. So there, appropriately plotted, is the points that we're going to join to create our first line. So of course, we get out our ruler. And sometimes this is tough to do on the whiteboard, we'll see. And we draw a nice big line that extends all the way across your graph. So there is our first line. Again, so make sure that your line is accurate, make sure that it passes through all the points correctly, and make sure you extend it because you don't know where it's going to intersect. Our next one will be a little easier to manipulate. X subtract y equals 4. We'll start by moving our x over. We're left with negative y equals negative x plus 4. Divide out by negative 1, or just switch your signs. So y equals x subtract 4, or x minus 4. So our y-intercept is at negative 4. So we start by putting a point there, and then we just go up 1 over 1, because the coefficient in front of x, of course, is 1. So now, Again, you line it up as best you can. And you extend your line all the way across the graph. And now we see a point of intersection, or a point of intersection is meant to be right there. Again, it's a little harder to do with the marker on this program, but you can see that that's where the point of intersection is meant to be. So the coordinates of this point are at 3 on the x-axis and -1 on the y-axis. So we are saying that the red line and the blue line intersect at 3, -1. So now let's see if that's right. So we need to check it with both equations. So we go to our top equation, and wherever I see an x, I'm going to substitute in a 3. And wherever I see a y, I'm going to substitute in a -1. And we're going to solve it. So we end up with 6, subtract 3 equals 3. And of course, 3 equals 3. So it checks out with our first equation, but maybe it doesn't with the second. Let's check. So where I see an x, I'm going to plug in a 3. Subtract -1 equals 4. So 3 plus 1, 4 does equal 4. So it works with both of the equations that we've found. Okay, so if you plot your lines accurately, you first have to rearrange them into the form y equals mx plus b, plot them accurately, find where they intersect, and then check using both of the original equations. Okay, and that's the method that you'll solve, or that you'll use for every single one of these questions. So in this particular problem, this linear system, the answer to x is 3, and the solution for y is -1. Let's do one final example, just to ensure that we have it. So with this, both of the equations that were given aren't in the form y equals mx plus b. So we have to do a little bit more algebra here. Not that that's a huge deal. But 2x plus 2y equals 6. We're going to move our x over first. In this case, our 2x. Divide out the coefficient in front of y, which is 2. And we get y equals -x plus 3. So we go up to +3 and we put a point. Now we're just going down 1 and to the right 1. So once we have our minimum of 3 points on there, we're good. So that means we get out our ruler again, and we ensure accuracy as best we can. And we draw a nice long line through the 3 points that we've identified. So there's our first line, our second line. 4x minus 6y, I'm just going to move my -12 over right now, equals 12. So I'm going to move my 4x over by subtracting 4x from both sides, which leaves us with -6y is -4x plus 12. Of course, we divide out the -6 across all terms, and it gives us y is equal to +2 over 3, x minus 2. Okay, so -4 and -6 reduce to 2 and 3, and since they're both negative, it becomes +2 over +3. So same drill now, we go down to our y-intercept and we put a point. We go up 2 to the right 3, and we can see where our intersection point is already. Up 2 to the right 3. So we get out the ruler. We, again, take the time to line everything up as best we can. And we draw our line. So what we've confirmed here, or what we can see, is that our point of intersection lies right there. And that point lies at 3 on the x-axis and 0 on the y. So it happens to be our x-intercept. And now we do our checks. So starting with the first equation, where I see an x, I'm plugging in 3. Where I see a y, I'm plugging in 0. So 2 times 3 is 6. 2 times 0 is 0. 6 does equal 6. So good start. Now over here, where I see x, I plug in 3. Where I see y, I plug in 0. 4 multiplied by 3 is 12. 12 subtract 12. 0 equals 0. All right, and the nice thing about this is it's the same format to solving every single linear system graphically. You put it in the form y equals mx plus b, put it in a form that you can graph, so you have to do some algebra to do that. You plot each line, being extremely careful to make sure that the lines are plotted accurately. You extend your lines because you don't know where they're going to intersect. Identify the intersection point. That will be the solution to your linear system. The horizontal coordinate will correspond with x, or whatever variable you've put on the horizontal axis. The vertical coordinate will correspond with y, or whatever variable you've put on the y-axis, or the vertical axis. Once you have your solution, you check it with both of the original equations, and that will confirm that your work is accurate.